Okay, so you took the data in the force interactive activity, and you got those calculations, right, for the acceleration. Did I do anything wrong?
No, I just got a 13.34.
Yeah, 13.34, that's going to be a rounding thing, right? You can tell what it really is, right? It's just a third, right? Okay, so, but yes, you should have this out so that you can correct as we're doing this. So some of you like put it away. So just, oh, don't turn it in. We're keeping it in your notes. Okay. Oh, that's a lot of people who didn't turn. Okay, come get these. Okay, so that's what you got. Can you tell me some conclusions? What did you notice?
The acceleration squared is half of the net force divided by the mass.
The acceleration squared? Where did you get acceleration squared?
Or, yeah, that's right.
No, this is acceleration. You calculated acceleration, not acceleration squared.
The acceleration is half the net force divided by the mass.
Ah, you noticed when you did question 9, right, that, whoopsies, that these were all the same, right? When you look at the net force divided by the mass, you get that, right? I'm sure as you were doing question 9, you didn't actually do all those calculations. I'm sure that you just saw the pattern, right, and got it. However, you used data to get that first column, right? And that data was about the velocity, right? And it showed you how the velocity changed over time, which is the acceleration. That's what we're going for, okay? So, change one thing at a time. So, for trials 1 through 6, right, these 2's stayed the same. It was the same mass the whole time. But we changed the net force. And then in trials 7 through 10, we kept the net force the same and changed the mass. But in all of those, did you use when you looked at double the net force?
2 and 3.
You used 2 and 3? Why?
Well, the net force is half, or be double from 2 to 3.
Okay, so these both had the same mass, so that's good. When we look at the double net force, we see that it went from 10 to 20, right? So that also, 2 and 4 is 20 to 60, that's tripling, and it went from 10 to 30. When we were talking about independent, who remembers what independent variables are? Maddie, what is it? Yeah, the thing that you change, but in science, you can't change all the things at once. You have to keep everything constant and only measure the acceleration, right? So this was the acceleration, was the dependent. For trials 1 through 6, we changed the net force and kept the mass constant, and then it was switched for the last couple trials. Okay, sound good? Everybody cool with that? Yeah. Awesome. So then we're looking at doubling the net force. Which trials doubled, right? So it doubled the acceleration, and you said you used 2 and 3? Okay. How about tripling?
2 and 3.
What's that?
2 and 4.
2 and 4? Was that right? There you go. And it tripled. Remember, when we say doubled and tripled, we're talking about multiplying, right? So doubled means times 2, and tripled means times 3. Yeah? All right, awesome. What happened when you looked at double the mass, though? Oh, it halved. That's right. So it halved, or times 1/2, or you could also just talk about dividing by 2, right? Multiplying by 1/2, dividing by 2, same thing, right? All right, and then what? So just for completion's sake,
3 and 9.
3 and 9, thank you. And what about quadrupling the mass? It was what? 1/4. Quartered. Right? All of these answers are okay. Divide by 4. Okay? And what, 7 and 9? Thank you. All right, why was it wrong to use, why couldn't we use 5 and 8? Joseph?
Because 5 has 80 net force, well, 8 has 40.
And they have different math.
Okay, but that is double.
Yeah,
They have
but they
different mass.
have, it's not the masses.
Ah, the masses were different. What was the mass for this one? For the 80 newtons, 2 kilograms?
Yeah,
And what was about this one?
5.
It was 5 kilograms.
Oh, wait, 5 and 8?
What was
Just 3.
3? You can't change both, right? Because the masses were different, you can't, I mean, you can, right? You can have 2 totally different situations with totally different forces and totally different masses, but you're not going to be able to make a conclusion about how the how the acceleration is affected by a certain variable. And that's what we're going for, right? Well, if I change the force and the mass at the same time, and then I measure something, I don't know why it changed. Was it because of the force? Was it because of the mass? What happened? So that's why we need to keep everything constant and only change one thing at a time so that we can really understand what we're looking at. Okay? Awesome. And the last question, right? We already filled out that table. So what can you conclude by this? Isaiah.
You divide the net force divided by the mass.
So the net force divided by the mass equals what? Acceleration. So guess what, guys? You just wrote down Newton's second law. Okay? This is Newton's second law. Pretty good, huh? You guys just proved it. Just doing that data, okay? You know, that's a lot of letters. I'm going to want some kind of shorthand, right? I'm going to want to write it in variables. So what do you think we're going to do? That's how acceleration is net force over mass. I want to write that equation in variables. So I'm saying, like, what's the variable for acceleration? Vanessa.
A equals F net over M.
Yay! Okay, this is Newton's second law, my dears. That's going to be an equation that you're going to use pretty often. All right?
So,
Yeah?
never mind. I get it.
Okay. By the way, you know how this is going to go. We're going to say, hey, here's a net force and a mass. Calculate the acceleration. And you'll be like, I got this. But what if I say, hey, here's an acceleration and here's a mass. What's the net force? What are you going to have to do?
The triangle.
The triangle. Right? You got to do a little algebra.
Don't say that. Just say triangle.
But it's algebra.
No.
But it's
Stop.
algebra.
Stop.
I'm going to write algebra.
I'm leaving.
You're leaving? Okay, so what are the other 2 forms of this that we might want?
A equals F lambda.
Lambda? What we got? Anna. Okay, mass is F net divided by acceleration. And what's F net? Yes, Lola. Mass times acceleration. And this is a form that you might have seen before. You might have seen like a meme, like a Star Wars meme that says, may the mass times acceleration be with you,
40.
right? So that's why, because force, right? So you might hear people say F equals ma, right? So that's a thing, that's a really common thing, F equals ma. But I want you to remember that it's really the net force. Now, we haven't gone too much into net force yet, but we will next class period. We'll get a little bit more into how to calculate net force. Okay? All right. How you feeling so far?
Are you gonna be all decked out for Star Wars Day?
Let's explore a little bit more. When we say that it's double the force gives you double the acceleration, okay? There are words that we use.
Where's the golf ball been? Why is it dead?
Okay, so acceleration is, this is a 2-word phrase.
Very fast.
Who knows, who can read my mind? Acceleration is,
Directly.
yay! Directly proportional.
Oh, that was correct?
Yes, good job.
Yay.
Directly, oh my gosh, I did not do that well. Directly proportional to net force. So, when we write A equals F net over M, one of the things that we say, sometimes if we're like, oh, what if I double the net force, right? What happens to the acceleration, right? Sometimes we do this little strategy with putting numbers in. So we say, okay, I double the net force, so I'm going to put a 2 here. And I didn't do anything to the mass, so I'm going to put a 1 there. And then to make this equation equal, I say, okay, let me look at these numbers. 2 divided by 1 is 2. And so I get 2 times the acceleration. Does that make sense?
Yeah.
Okay, these are called proportionality problems. We've done these before, I feel like.
Yeah.
Yeah, but it's been a while, so totally fine. Okay, cool. So that's directly proportional. Who knows what's coming next?
Indirectly proportional.
It's not indirect.
Not so.
Not very proportional, no. Inversely.
Acceleratory.
Yeah.
Wow, not even close to a word. Okay, what is acceleration inversely proportional to? Mass. So, let's do this again.
Versatility.
Let's get our red going on. Okay, so now I'm not changing the net force, but I'm doubling the mass.
Oh, 1 divided by 1.
Look at that!
Whoa.
So now,
Oh, is that why it changed when you doubled the mass?
yes. So when I doubled the mass, I have
Acceleration.
half the acceleration.
And then if you triple it, then it'd be a third.
Yes, great job. Now, so this is what you just mathematically showed, right? But let's back up for a second and make sure that this makes sense in our brains with our real life, okay? If I double the net force, if I push harder on something, it's going to have double the acceleration, right? It's going to get to a faster speed in the same amount of time. Does that make sense? Right? Like literally, that's kind of a duh, right? That's like a, oh, you push harder on something and it gets faster? Okay, right? Cool. How about the mass? Who can sort of reason through that mass? Malia? Yeah, so if it's going to be, you want to keep going, Isaiah? Go ahead.
Yeah, with like for the cart thing, it said if you add blocks of concrete onto the cart,
Yeah?
what will happen to it?
Yeah.
Slower.
Yeah, so this is just your daily life, right? If you're in the grocery store and you have an empty cart and you push it, right, it'll go flying, right? But if you have a full shopping cart and you push it, right, not so impressive, right? And that's because mass is a measure of,
Gravity.
what did we talk about last time? Starts with an I. Inertia. Mass is a measure of inertia, which means it is more resistant to change in motion. Does that make sense?
Yeah.
So if I have a bigger mass and I exert the same force on it, it will not have as big of an acceleration because it doesn't want to change, right?
Change is good.
Change is not good for masses,
Needs to change.
right? Nature hates change, actually. That's kind of a law of physics, really, is that nature hates change. Okay?
Well, change hates nature.
Change hates nature. Okay. All right. Hold on. When we look at A equals F net over M, we're looking at which are vectors, which are scalars. Acceleration is a vector and net force. Very good. And what's a scalar? Everyone? Mass. There you go. Because honestly, right, what does it mean to have like 2 kilograms that way? What? Right? That makes no sense. So this has no...
Okay, you don't suck anymore. Good job. Really good.
Okay. So yes, the vectors have direction, scalars, no direction. So yes, dir, yes, direction, sorry. Oh, yes, dir, okay. So this comes to our final point about Newton's second law, is that the acceleration is in the same direction as the net force. So remember, acceleration can have a direction. So if something's slowing down, where do you think the net force is pointing? Exactly, the opposite direction of that motion. Does that make sense? So when we thought about our book and it was sliding, it was moving this way, but the friction was the other way, right? Because it was slowing down. Okay? Yes?
That doesn't make sense if it's in the opposite direction as the net force. Why did you write the same? Or
No.
is that
Sorry, the acceleration is in the same direction. But
net force
listen, I was talking about when something's slowing down, the acceleration and velocity are in opposite directions,
Oh.
right? And so I'm saying the net force is in the same direction as the acceleration.
Okay.
All right.